Hello again. This is the second recording for Wednesday, February 13th. We're going to take a look at section 6 out of module 2 that has to do with rational functions and asymptotes. I'll apologize ahead of time if I find myself coughing here and there. I'm trying to get out of a cold. You guys know that already from yesterday. I'll try to be good on the recording here. So I may press pause a few times while I'm working on this. All right. So what is a rational function? First of all, when we think of the word rational in terms of math, it doesn't mean logical or sane or well-reasoned or anything like that, like you would think of rational in the English language necessarily. Rational in math means if a number is rational, that means it can be written as a fraction. Okay, it either is a fraction or it could be written as a fraction. All right, so all fractions are rational and all integers are rational because -3 can be equal to -3/1 and so on. And decimals that terminate or repeat are also rational. All right, so that's how we define rational numbers. Now, rational functions uses the same idea. Rational functions are basically written in the form of a fraction. A rational function is the quotient of two polynomials in the form f of x equals p of x divided by q of x. Okay, so there's your function. P of x and q of x do not have factors in common, and also q of x cannot equal 0 because it's in the denominator. All right, so the interesting thing about rational functions is that there are values of x that oftentimes will make the solution undefined at certain points. All right, in order to look at that and how we deal with that as we graph this, we're going to take a look at an example. It's probably the most basic example of a rational function that I can think of, and that is f of x equals 1 over x. Okay, now there's an x in the denominator. Remember, we cannot have division by 0 in the family of real numbers, within the domain of real numbers. And so at x equals 0 itself, f of x is going to be undefined. All right, so that means that there's going to be some sort of a break in the graph when we graph this. All right, it's not going to be a continuous graph like most polynomial functions are. If it's a rational function, generally speaking, it is not continuous. Anyway, f of x is defined at x equals 0. As x approaches 0, from the right, though, as long as x doesn't actually become 0, f of x will have a legitimate value. So let's say let's say we start on the positive side and we approach 0, so the values of x get smaller. All right, so if x equals 1, then f of x equals 1 because 1 divided by 1 equals 1. If x equals 0.5, then f of x equals 2. And as if x equals 0.25, then f of x equals 4. And I think you see the pattern. As these numbers get smaller, the value of f of x gets larger. All right, so f of x will continue to get larger as x gets closer to 0. Now, we can get really, really close to 0 without actually being at 0. Okay, we can have 0 point and then have 1,000 zeros and then a 1. That's not 0. All right, and so f of x will have a value. It will be basically infinitely large. Excuse me. All right, so that is when we approach it from the right side. If we approach from the negative side, from the right, as x approaches from, that should say from the left, sorry, as x approaches 0 from the left, let me change that. Or negative side, then f of x is going to get smaller as x gets larger or closer to 0, and will get infinitely small. So if we're going from the negative direction, these should all have negatives in them. Let me change that as well. All right, so the numbers are actually getting larger. They're getting closer to 0. Then the f of x values are going to go negative. And they're going to get more negative, or they get smaller, in other words. And so it basically will approach negative infinity going in that direction. Well, how's that going to look as far as what our graph looks like? Well, this is what the graph looks like. All right. Like I said, the graph of a rational function is not going to be continuous. It basically has two pieces to it. Okay, the two pieces, I believe that's green. I don't know. I don't think I'm colorblind, but I think that's green. Okay, so that curve here is part of the graph of f of x equals 1 over x. But this curve here as well is also a part of that same function. Okay? And this red line is the line. In this case, it happens to be the y-axis, or x equals 0. Wouldn't have to, of course, but in this case it is. And that is the line where basically we have where the function is undefined. All right, and what that line does is it basically sets off a border that helps us graph the actual curve of the function. This line is called the vertical asymptote. And there is a P in there. It is sometimes it's hard for me to say this word and not pronounce the P, asymptote. Sometimes I swallow that P. Sorry about that, but that's what the word is. I think you know what an asymptote is from Algebra 2, but it is good to be reminded of it, because we will be seeing more of these as we go along throughout pre-calculus. Now, if you look at this, we have that vertical asymptote where we have an undefined function. If we look at it, though, we seem to have another asymptote that is horizontal. And in fact, we do. We notice that this curve approaches this line, which happens to be the x-axis, or the line y equals 0, but it doesn't actually touch it. And the same going in this direction. And so we also have a horizontal asymptote at the x-axis, or y equals 0 in this case. One of the things you want to be able to do is determine where the vertical asymptotes are going to be located and where the horizontal asymptotes are going to be located. All right, and we have a rule for that. All right. Basically, when you are trying to figure out where the vertical asymptotes are located, what you want to do is you want to take a look at the denominator, the q of x, and you want to factor that if it's possible. And that's going to help you find the zeros of that function. Okay, that will give you the values of that function that will make the denominator 0. And so you will have 1 or 2 or sometimes no zero vertical asymptotes, but those are the locations where those are going to be located. All right. So the vertical asymptotes basically are found with the denominator. Though the numerator doesn't really have much to do with the vertical asymptotes, but the numerator does have something to do with the horizontal asymptotes. Now, the horizontal asymptotes can be found in 3 steps, and it has to do with the polynomials if they are written out in polynomial form with the leading coefficient and the leading, basically the largest degree in front, writing in descending order. Okay, so we would have the value that is going to be important for figuring out the horizontal asymptote is going to be the exponent that tells us what degree that polynomial is. So, for example, if this value of n was 3 and this was 2, then the numerator would be a cubic function, cubic polynomial, and the denominator would be a quadratic polynomial. Okay, so those two numbers, the n and the m, are going to be important for figuring out if there are horizontal asymptotes, and if so, where. Here's the rule for that. If n is less than m, then the x-axis is a horizontal asymptote, or the line y equals 0. Okay, that was what happened with the previous example. The x-axis was the horizontal asymptote because the numerator had a degree of 0 and the denominator had a degree of 1. Now, if they are the same, like for example, if both of these were cubic functions, then the line y equals a of n over b of m is the horizontal asymptote. In other words, these two leading coefficients. That's going to be the line y equals that that fraction a over a of n over b of m. That will be your horizontal asymptote. And finally, if the numerator degree is bigger than the denominator degree, then the graph does not have a horizontal asymptote. Okay. So those are your rules for that. Whoever's running this can pause this for a second, give you a chance to write this down. When you guys are ready, please let him or her know, and you can continue. All right. I'm going to have you try a couple in class here. I'm going to have the teacher in a second pause the video and let you guys have a chance at this. We have 2 rational functions below. For both of them, I want you to try to figure out what are the horizontal and vertical asymptotes for those functions. The first one is 3x squared minus 5 over 2x squared minus 8, and the second one is x minus 10 and x over x squared plus 5x plus 4. For both of them, see if there are horizontal and vertical asymptotes, and see if you can find that. Whoever is running this may pause the video for a second and let the students try to figure this out. Students, make sure you give the teacher some indication that you have an answer or that you don't know at some point. Okay, so let's see what you guys got. What you got for answers. For the vertical asymptotes, you need to factor the denominator. All right. So the first one, we have 2x squared minus 8. We can factor out a 2, so you have 2 times x squared minus 4. That's a difference of squares, so that's 2 times x plus 2 times x minus 2. So that tells us that positive, negative 2 are going to be where your vertical asymptotes are, and those are located right here. Okay. The degree, 3x squared and 2x squared, are the same degree, so the horizontal asymptote is going to be located at y equals 3/2, and that's basically drawn right here. It's a horizontal line at 1 1/2, and that's where the horizontal asymptote will be drawn. For the second one, we have x minus 10 over x squared plus 5x plus 4. We have a horizontal asymptote at 0 because of the degree is greater in the denominator, so basically it's the x-axis.